Good afternoon. We're back on. We have people here in the room. So we are here at Xylexpo Arena at the biannual woodworking industry fair. And this is our third appointment of this cycle. This is taken care of by the SISEF group, so the woodworking technology group. As I said, Giacomo Goli is going to talk about tools, especially cutting speed and feed speed. Thank you for being here, Giacomo. You're going to see your slides on the computer screen here, and thank you. The floor is all yours. Thank you. Thank you. Thank you, Giacomo. Thank you to everybody who's here. My name is Giacomo Goli. I'm Professor of Woodworking Technology and Forestry Technology at the University of Florence. With colleagues, we have been working for a number of years on this issue, cutting forces. So we thought it would be interesting to give you this presentation about the configuration of cutting and feed speeds in wood material processing. I thought I would be able to point at items on the presentation, so it's going to be a bit messy for this reason. I apologize for that. And to talk about woodworking, the first thing to do is to know wood. Wood comes from forests, very peculiar material for a number of reasons. Wood is a functional material. The function of wood is to let the tree grow and let it grow in height and to sustain leaves that perform photosynthesis. So I have branches, leaves, a number of issues. But this also gives opportunities because wood is a biogenic material, which means that it does have a special relation with CO2. So it's very advantageous from an environmental standpoint when you do life cycle assessments of wood-based products or wooden products. It's a hierarchical structure, strongly anisotropic, and this structure characterizes wood considerably, which is very important when working it. Wood species, you saw it below on the right, about 80,000 different wooden species in the world. And the panorama is very varied. Cocobolo, 1,260 kilograms per cubic meters density. Balsa is next to it, 150 kilograms per cubic meter. It's like comparing stone to polystyrene. So all different. Each individual species has got its own anatomical characteristics determining behavior, including density. Wood does have many defects. These images made available by Microtech. You see knots, for instance, or cracks, so fissures, worms. The black tunnels there are insects digging tunnels. So we do find a lot of weird, irregular things inside wood that we have to consider when we're going to work it, mill it. We also have to consider that a single species can have highly different characteristics. On the left, we have American Douglas fir, 14 rings per centimeter. The European Douglas fir has 1 ring per centimeter. So that density and growth characteristics are so different that there are almost different species, but they are same species. So this, you have to consider all this when thinking about woodworking and thinking about configurations, we can have two approaches. A purely geometric approach based on cinematics of woodworking, and a more mechanical approach that we have been working a lot recent years, and we have developed studies talking about cutting speeds and forces. What is important here is wood density, humidity, moisture of wood. We have developed a model based on 11% dense humidity moisture. We're talking about wood, we have to think about the orientation of the grain, the type of tool. A disc will do a lot of load, but will take a lot more time getting cold. The type of cutting material, the way the cutting tools are clamped, are fastened to the body or clamped to the tool. Let's think about the simplest cutting manner, so free orthogonal cut. You see here we have the cutting speed, the chip thickness, the cutting width, and the cutting length. This is the easiest type of cutting. And in this model, I'm showing you how wood behaves when it is recorded by a high-speed camera. You see it's longitudinal, and the knife is cutting very well here. It's 15 kilohertz, frames per second, basically, 15,000 frames per second. If I put the grain slightly tilted in the direction of the cross of the grain, of course, in these working conditions, the cutting edge exercises totally different strengths than it would, or forces, than it would when working cross grain, which I imagine you all are very well aware of it, but you really see what happens in these pictures. And when we talk about forces, we see the differences, two extremes, longitudinal cut, the last is cross grain. Here on the left we have shear forces for beech chips. So 0-180 are cross grain profiling. The strength needed to cut beech, 0.091 thickness, the darkest line with the circles is 5 newtons per square millimeter of section, whereas when we go crosswise it's double. So if we work crosswise, the strength is about the double than when we work in longitudinally. If you look at the right hand chart, poplar wood, poplar is less dense, so different strengths, lower strengths. So different types of species can produce higher or lower strengths. We can calculate the strength of cutting a chip. You see that with beech, 0 degrees, you need 150 Newton force, like 15 kilograms to push it away, whereas perpendicularly you need 300 newtons, 30 kilograms. When we talk about poplar, the values are lower, 100 and 150 newtons. Here too, I would have liked to be able to point, but from here it's easy to calculate powers from strength. Power is strength multiplied by speed. So force by speed gives us the power that we need to do this job. You see that with poplar, work at 25 meters per second speed, 3,750 watts are absorbed. If I'm going faster, 50 meters per second, I need more power, 7,500 watts. If I work perpendicular to the heads, so 25 meters per second, the power needed is 7,500 watts. And so on. How does the cutting speed impact? So the more heat, the faster I go, more heat I create, the more the tool is gonna get hotter and hotter and get to worn out much faster. That's why speed ranges are advised. For instance, with soft wood, we talk HM millers, we have 60 to 90. Whereas when we talk about hardwood, we have to go at slower speeds because otherwise wear and tear would be much faster. And so on with all the types of materials, wood-based. Okay, we did tests in France. We stayed there 2 months. We also had a bicycle with wooden panels below. And as part of this project, anisotropy, sponsored by the University of Florence. And I would also like to thank Gianluca Fantacci, who made 3 special millers just for us, or cutters just for us. And how does the model that we developed work? We have 4 entry variables: the grain angle, wood density, actual angle of the knife. It can be straight, tilted 15 degrees or whatever. And the working mode, up milling or down milling. So up milling or down milling, explained in Italian. Here on the chart here, you say 90 is head woodworking, working on the head of the wood, and the cutting coefficients here are higher. So 90, lambda 3 and lambda 0, the straight blade, produces a coefficient of 55. Lambda is tilted at 15 degrees. The coefficient yielded is about 40. I'm saving 40% of the force simply by tilting the edge of the knife. If instead my lambda is 30, so 30 degree axial angle, forces are halved. So same cutting speed, half the power. So here I need half the power than I need when using a straight tool. I could spend hours, but what does the model tell me? 2 coefficients, Ks and int, and my formula is F, the thickness of the chip, L, the width of the chip, and it tells me what force I need to cut the chip. Graphically shown here on the top, I have grain orientation 90 degrees. Chip thickness 0.1 mm, chip width 30 millimeters, density 740 kilograms per cubic meter, cutting velocity 25. Then, depending up milling, down milling, the different lambdas, I have up peaks and down peaks that change. So, but just by using the formula, just changing the lambda of the tool, of the milling tool. in terms of grain orientation, GA0 degrees, you see that powers on the right. So I'm using much less energy here, power. This an introduction to show you how it works. Let's try to apply it to a rotating tool. This is a simplified version for orthogonal cuts. Let's apply it to a rotating tool. The chips that are produced here are weird. They are cycloid arcs with zero thickness on at one end and the highest width at the other end. So I'm going to have a number of chips, the thickness of which is not going to be the same. So here we're going to need to calculate the average thickness of the chip. And since it's cycloid arcs, I'm going to leave the surface all striped by those cycloid arcs. Here we have a number of factors coming into play. I'm not going to list them, but we have time, so. So it's various factors, and we have the number of dents or tooths. Theoretical rugosity, a number of roughness, and I've created 3 working conditions. An end mill cutter, a profiling cutter, and then a planer with different speeds. You see that these 3 different working conditions immediately produce very different cutting speeds. In the first case, it's 16 meters per second, which is very low. And I'm talking about the end mill cutter. So, and here we're talking about 15,000 reeds per meter. Second case too, larger diameter, creates higher velocities or speeds, but they can still increase them. The planing shaft instead, we're already talking about 141 meters per second, so it's quite a lot already. So looking at cutting speeds here, I can decide whether I can work at higher reefs per minute or not. Another problem is feed speed, which is the purpose of this presentation. So I set for all 3 working conditions or methods 10 meters per minute as the feed speed. And feed speed, of course, wood moves, and my tool rotates and cuts chips. In this case, we're going to calculate feed per reeve, F, which is quite an important parameter telling us how far, so what's the feed for each reeve. Feed of the tool. Why this is important? Because the more the tool cuts chips, the more the feed, the longer the stripes, the higher the crests, and the more it will be visible geometrically by the end user that will see it as a bad, ugly surface. F, that we've just seen, is a parameter, but what matters the most is Fz, that is, in the time of one reeve, wood is moving on, but more cutters, more knives, I can cut more chips. Fz is the feed per dent or per notch. So if you look at the end mill cutter with 2 FZ, the cutter to the planing shaft Z4. So the FZ is the same for the cutters, but now it's different for the planing shaft, the 0.21. This is helpful to see. These are lathes or Vivaldi tools data, but they define the quality. As you can see, 8. If I have fine quality to them, it goes from 0.2 to 0.4 millimeters. So if my FZ is between this range, I will have good fine quality. If I increase FZ, I will see those waves, and so quality decreases. So setting the feed speed can be done geometrically using the FZ formula to obtain the FZ I need. If I need to make a beam that is going to place 20 meters high, I can use, I can have less fine quality. But if I want to have a manufacture like this, and it's going to be an object, an item to be held in a hand, then I need very fine quality.
Another key factor is how tall the crests are compared to the plane, to the lower plane. In my drawing is RW, so the waves, how much is the height between the bottom part and the upper part, RW. This is another easy to calculate parameter. If this parameter is below 1 micron, as in the case of the cutter and the blade, you can barely see it. Whereas if you have the end mill cutter and RV is higher than 1 micron, then you can start appreciating and seeing these crests. I've tried to develop a graph, and this is a simulation of a surface obtained with processing with 5,000 revolutions per minute and 6 meters per minute. So what happens if I double the feed speed and the cutting speed? Nothing really happens, because if the RPM and the feed speed is the same, my final surface will be identical. If I work with 6 meters per minute and 5,000 revolutions per minute, when I double these two parameters, I will obtain the very same result. So if I have a surface that I'm satisfied with, but I want to increase my productivity, I may as well increase the revolutions per minute together with the feed speed and still have the same result. What happens instead if I increase the VF parameter, speed, feed speed? FZ also increases, and this happens, the surface becomes more irregular, and so there will be all these waves that are visible, more visible. What happens if I double Z as a parameter? So instead of using one cutting edge, I use two cutting edges. Well, the result in graphical representations will be this one, so with a more regular surface. What happens if I increase the diameter of my tool and all the other parameters remain the same? Well, in this case, this is what I will obtain, a better surface, a better quality surface. With small tools, I may have unsatisfactory surfaces, and so I can improve its quality simply by increasing the tool plane parameter. Another aspect that I can calculate, and I can do this with these formulas, is the chip thickness, H max. As you can read, in the case of the end mill cutter, it will be 3/10. In the case of the blade, it will be 6/10, so much smaller. However, when you calculate the cutting forces, we need the average chip thickness, which is very easy to calculate. You take the HM and divide it by 2. And this is what you obtain, the average chip thickness values. An important point I'd like to make are the fastening system. If I have a mechanical fastening system, in order to insert a shaft inside another shaft, I need to have some room to play with, at least 5/100th. So I will have a run out at least equal to 0.05 m. So the average chip thickness in my blade is 3/100th. So it's much smaller than the run out of the shaft. So if I have 2 cutting edges, 2 tools, in these conditions, only 1 cutting edge will be able to work. If I have an hydraulic fastening, which is much more accurate and produces much smaller run out, 2 microns, 5 microns, I will work much better. So a conventional shaft, or spindle, will have only 1 tool, 1 cutting edge to work, and so my FZ will be very high with an ugly looking surface. With a hydraulic fastening system, I will use more cutting edges, not all of them though, but still FZ will be better looking surface. Whereas if I use all the cutting edges on my machine, after inserting the shaft, well, all the cutting edges will be aligned, and the quality of my surface will be very, very good. So by using the model I showed yesterday, we can calculate the force that it's required to cut these chips for end mill cutter. It's 385 newtons. If I use a beech with a 45-degree grain angle and a width of 40 millimeters. Similar conditions for beech wood, straight cutting edge, I would use 412 newton. Whereas in the third case, with the blade, if I cut along the grain with a 15-degree axial angle, I would obtain 15 newton in terms of required cutting force. So this allows us to calculate ultimately the cutting power. In the end mill cutter, I will use 6 kilowatts to perform this job. For a normal mill cutter, I would need 14 because I have a straight cutting edge tool, whereas in the third case with the blades, I have a number of factors that allow me to just use and consume 2 kilowatts only. So as I get to the conclusion of my presentation, I'd like to underline that I've tried to select the most important aspects in determining cutting speed and feed speed. There are geometrical criteria or formulations that I can insert in an Excel spreadsheet and then can provide me good guidelines and input for setting up this type of woodworking processes. I can also adopt mechanical models that can allow me to calculate the cutting force and power, and this gives me input whether I need to increase or decrease the feed speed, whether I am working with higher or a smaller chip thickness. So whoever works with wood needs to be proud to be able to work and interpret a material that it gets extremely complex and heterogeneous. Metals are much simpler to be worked with. And wood is also material that has a unique environmental characterization or profile, and from the point of view of environmental friendliness, it has nothing to learn from any other materials. If I just may add, I was very quick. We still have time. I was afraid I would bore my. I would tire up my audience, so I tried not to be too long. I'd just like to point out that at the University of Florence there is a graduation program in technology and advanced transformations for woodworking, wood furniture suppliers and building wood. This is a graduation program that provides a lot of knowledge about wood and its use, microscopic identification, scientific methodologies, wood and wood derivatives, characteristics of the wood species, technical standards, solid modeling. There is a training course on building structures in order to be able to have a conversation with project planners. We also offer design training programs so that our graduates can also have a conversation with the designers. And you can check all these options on our website under the chapter Didattica, teaching offer or educational offer. You can certainly find all the details of what we offer. Thank you so much for the attention. I finished a little bit earlier than expected. And of course, this is useful because we have time available for questions and answers. I am extremely curious because something that it really looks very banal, like getting a piece of wood run over a piece of metal, can actually trigger this multitude of data. I know that the most careful and experienced manufacturers are very much in line or oriented to your thinking. How did you come about it? Well, I am a wood technologist, so I'm very well familiar with material anisotropy. And I was in a company, and one guy once told me I was working wood in a longitudinal way, and then I tried the cross-grain type of working, and I realized that it is much better. And these are people that work on a machining center on an everyday basis, but they sometimes lack this knowledge. And also engineers sometimes don't have the ability to understand the heterogeneous characteristics of wood and its anisotropy. So velocity forces are more related to panels rather than solid wood, possibly. Well, working a wood panel is much simpler. This material is much more isotropic, and that's fine, easy. We ran tests. We ran a lot of tests to calculate all these parameters, also for panels, specifically plywood, cheap boards, and MDF panels. Yeah, my question is, are there manufacturers that are still lagging behind and still need to fill the gap of knowledge and pushes this type of research? I think that data that has been shown today are fundamental to have a conversation with whoever manufactures cutting tools. Otherwise, it's just a style exercise. Well, this type of exercises have been conducted for 1,000 years on metals. All the calculations for shear forces in metals is there, whereas it was lacking in the field of wood. We did something very innovative here. We have already established contacts with cutting tool manufacturers, and we have connections with them. We would like to start a conversation with the tool manufacturers that are associated to ASIMAL to deep dive into this topic. I think we have a group of a high number of cutting-edge tool manufacturers that are members of ASIMAL, both for solid wood and for wood panels. So I believe that if we can intensify this conversation, both sides will benefit. So the association behind the Expo exhibition and all the communication platforms will really try to put all these stakeholders together and really ultimately get to work together, and we have the possibility to really rely on you and your knowledge. So I think I can say we maybe can organize a webinar to present your data, your calculation methods, and maybe we can maybe you can convey the benefits and the advantages of this theory. I think the end users will highly treasure these pieces of knowledge. Otherwise, they will put pieces of wood in the wrong way, in the wrong direction or orientation. Yeah, they can set up their process in a more optimal way. And sometimes with manual machine, it's easy to learn. But with CNC machines, if you can rely on a tool that helps you in setting up the machine in the most optimized way, I think it's important. So going back to tool manufacturers, I can mention Gianluca Fantacci, who is the president of the tool makers group at ASIMAL, and he pushes us to work a lot. Many customers call him and they ask me, how am I supposed to set up the feed speed or the cutting speed? So developing an application, developing a tool that helps me select the type of material, poplar, available speed from the machine, how do you work it, what settings do you have available, or what is the power of your engine, and what is your targeted quality, and an app can give the right guidance. If the rotation speed is maximum 12,000, well, and you can adjust the other parameters. I think with this system it's also easy to calculate the power. As far as I know, there is nothing similar in the woodworking industry, and I believe it would be greatly helpful to the end users. Absolutely, absolutely, I agree with you. I have to be honest, I didn't follow you through completely. It was kind of hard to grasp all your input. However, it is highly appreciated. I think the message we have here is very nice. All in all, access to knowledge can be made simple, can be simplified. Through a simple app, many problems can be overcome. I think I like this idea very much. So I think that this cycle of lectures sponsored by and organized by SISEF are really highly valuable. I think we will have additional occasions in the future to meet again.